let's spend the last 15 minutes, keep looking at the clock, 10 minutes, doing an example of how we calculate fugacity for a saturated vapor or a saturated liquid. What's the difference between the fugacity of a saturated liquid and a saturated liquid? They're equal, exactly. If we have saturated something, I have two phases in equilibrium. That means equality in gift free energy. That means equality in fugacity. So if that's the case, and I'll do an example with water where we have steam tables. I'll do an example from your text. So let's look at illustration 743. So we're asked to compute the fugacity of saturated steam at 300 degrees C. Why am I not specifying a pressure? No, it's not zero. It's definitely not zero.
It's fixed.
It's fixed. Why is it fixed? How many degrees of freedom do I have? Exactly. Saturated. Saturated means two phases in equilibrium. The vapor pressure curve specifies if you have a temperature, there is a unique vapor pressure. Okay? How do you find at any temperature the vapor pressure of steam? Steam tables. Or you can use a Unison model to look at. So if I pull out the steam tables that are at Appendix A of your textbook, first you see saturated steam. And if you look at saturated steam, you find at 300 degrees C, the pressure, the vapor pressure is 8.58 megapascal. So from saturated steam table, page 918 on your text, at 300 degrees C, T, which is the vapor pressure, is 8.58 megapascals. And we can calculate the fugacity. We're going to use the definition, fugacity equals pressure, e to the 1 over RT, G minus G ideal gas. How we calculate G? The table has H hat and S hat. So first calculation of G. That's the easy one. Okay? Table gives H hat, S hat. You just read the values from the table. Okay, I don't have much time, so you'll allow me not to write those numbers. But from here follows that G hat can be calculated as H hat minus TS hat. So G is going to be G at 300 degrees C and 8.58 megapascals is calculated. How? This is per kilogram. If I want to do it per kilomole, what do? I multiply by the molecular weight. So that's 18.02 times G hat. And I will give you the number for this one. the result is minus 9376.8 kilojoules per kilomole, which is the same, of course, as joules per mole. So this is how we find G. Now, how do we find G ideal gas? It has to be G ideal gas at the same temperature and pressure. So need G ideal gas at 300 degrees C, 8.58 megapascals. How am I going to get this? The idea is the following. You want to have, first of all, at 8.58 megapascals, this is not an ideal gas, right? This is the real substance at those conditions is not at all ideal gas. Any substance becomes ideal gas as pressure goes to zero. Use the temperature 300 degrees C and go to the lowest pressure you can find at that temperature, 300 degrees. So I'm going now to the steam tables, but different steam tables, not the saturated steam tables. Assume G ideal gas at 300 degrees C, P lowest is equal G at 300 degrees C, P lowest. P lowest is the lowest I can find in my steam tables, the lowest pressure. So now it's no longer saturated steam. So your steam tables first have tables on saturated steam. After the table of saturated steam goes for superheated vapor. That's superheated vapor. So if you look at superheated vapor, you can see it has at different pressures, different temperatures. You may have to interpolate some. In this case, 300 degrees C, I don't. The lowest pressure available in steam tables, at least in your text, is 0.01 megapascals, which is 0.1 kilopascals, in other words, 0.1 atmosphere. Okay? So, lowest P available in steam tables, in text steam table, I cannot tell for others, is 0.01 megapascals, which is 0.1 bar. Okay? Well, at 90% vacuum, it's not unreasonable to assume that it's ideal gas. That's a pretty good assumption. At that lower pressure, things behave ideally. So we make the same calculation, get H hat, S hat, calculate G hat is H hat minus TS hat, calculate G ideal gas at 300 degrees C, and now 0.01 megapascals as 18.02 times that G. Okay? So I go now at 300 degrees C, different steam tables, superheated steam tables, superheated steam. This was saturated steam. Okay? And this is, I'll give you the answer for this. If you do that, the answer is minus eight 221.6 kilojoules per kilogram. So we have G ideal gas at 0.01 megapascal. We need G ideal gas at 8.58, same temperature. What's the relationship for G ideal gas changing the pressure? G ideal gas at 300, 8.58 megapascals. Because it's going to be a ratio of pressures, I don't need to do conversions, but otherwise multiply times 10 to the 6 to get pascals, equals G ideal gas at 300 degrees C, 0.01 megapascals, plus integral from 0.01 to 8.58 of V molar ideal gas, right? dG is partial G with respect to P is V molar dP. You should know that, right? Remember that? And what is V molar ideal gas? It's RT over P. RT is, this is at constant temperature, 300 degrees C, everything. So this is RT ln 8.58 over 0.01 and remember this has to be Kelvin. If you plug in the numbers you get, oh, oops, I apologize guys. This is the minus 8221, not this one, sorry. Erase that. I don't have this written. I have written this. This is minus 8221.6 kilojoules per kilogram. Finally, now I have those. Plug it into this definition. Okay? So now I have G ideal gas at those conditions. From the saturated table, I had G at those conditions. This was G at those conditions. This is G ideal gas at those conditions. Plug into F equals P. And what is the P? 8.58 times 10 to the 6 pascals, right? E to the 1 over RT, G minus G ideal gas. And the final answer that you will get is 6.7 megapascals. One thing you should always do, check if it makes sense. We're talking about vapor approaching equilibrium. Remember the program. What did the program show? It starts slope 1 and then curve downwards, right? What is the pressure I have? 8.58 megapascals. What answer did I get? 6.7 megapascals. That's reasonable. If it was straight 1, it would have been answer 8.58. Curving down will give us somewhat lower than 8.58. But if I've got an answer 0.1 megapascals, something is wrong. I've got an answer 10 megapascals, something is wrong. Okay, so clear how you calculate this fugacity? Okay. This is important because as you will see, in calculating fugacity of the liquid, the first step is to calculate the fugacity at the vapor pressure. And then you proceed from there. Oh, sorry. Check it, okay.